Andrzejewski. So this is the first complex task for me to pronounce some of these names more or less correctly. So you have 8 minutes from now.
All right, thank you all for coming. She said, my name is David Andrzejewski. This is a continuation of work I did as part of my PhD at the University of Wisconsin with my advisors Xiaojin, Jerry Drew, and Mark Craven. Also Ben Recht from the University of Wisconsin. So before I get into anything, we're going to be talking about, we have LDA, this latent Dirichlet allocation topic model, and we're going to include domain knowledge into it in a very generic way with first order logic. So the first task is to explain LDA in one slide. So just very, very high level overview, what latent Dirichlet allocation is going to give you after you run it on a corpus of documents are these topics, phi. Each topic is a multinomial distribution over the vocabulary. So here I've shown each multinomial distribution as these series of bars, where longer bar is higher probability. And they're called topics because typically these clusters of words correspond to human interpretable semantic themes. So these topics are hypothetically learned from some corpus of biomedical documents. And you can see this first one is kind of about embryonic stem cells. It's putting most of its probability on those words. The next one is kind of about patients and risk and medical factors. Most of the probability is there. And the last one is about the drug resistance. And that's the high probability words for that topic. So then each document is modeled as some document-specific mixture of these corpus-wide topics, and where the mixture weights are given by theta. And again, I'm just showing these bars kind of loosely proportional to these probabilities. So this first document, you can see it puts most of its probability on the stem cell topic and this patient's risk topic. The next document is kind of a mixture of patient risk and the drug resistance topic. And so you learn these topics, which are interesting in their own right, and these document topic associations. Finally, you have the actual observed words, W, which is all you have at the beginning, and kind of the latent topics associated with each word, which sort of act as loosely interpreted semantic tags on each word. So here, patients and risk come from that topic, drug resistant come from the other topic, and we have this explanation. So LDA is a whole topic unto its own right, and the most important thing to say here is that it learns these topics and these associations from the data itself. And why would we want to do this? There's all sorts of cool applications. For example, in this work from UMass, they plotted the topic popularity in, I believe, NIPS abstracts versus time. So you can kind of see neural networks had a spike there, and then it kind of went down, and then maybe if they continued out to the present day, it would be back up, and this kind of thing. You can use it to do information retrieval by associating the topics with documents and augmenting it, like in this UMass prototype. Also, if any of you are going to be at KDD in San Diego in a few weeks, I'm going to be presenting some work using topics for information retrieval there as well. You can also do some really interesting work studying the process of science itself. You can associate topics with individual authors and see how they influence other authors or other documents. You can use it to try to create a system matching domain experts to which paper they should review. So this is just kind of the tip of the iceberg of the cool things you can do with topic modeling. But as I've described it so far, the base topic model, LDA, is completely unsupervised. Those topics phi and the document topic associations theta are learned completely from the data and nothing else. So there's a whole literature, and anybody who's worked with LDA can tell you, this can lead into problems where you learn topics that are not exactly what you had in mind. They're purely statistical artifacts, really, and associating them with topics is kind of something we do after the fact. So this can be problematic, and people have come up with a wide variety of ways where they've extended the basic LDA model to try to take into account label information, image information, or these other things to try to steer the topic. But to extend the model, you kind of have to be a bit of a machine learning guru yourself. So we're going to be looking at a way to have just a general mechanism to let non-graphical model experts insert their domain knowledge into LDA. An example domain knowledge might be that these two words do not belong in the same topic. If you look at the learned topics, you might say, this one is really mixing up two different concepts. It's got stem cell and patient risk, and I don't really want those together. You might have a predefined topic in mind that you want to kind of build a statistical topic around. You might have document labels that you believe should have some kind of influence on the topic. You might have delicious tags on web pages that you want to associate with topics, and you don't want to let documents with this tag use that use this topic or that kind of thing. You might have topics that you believe are completely incompatible. So this one is about the Iraq War, and this one is about the Afghanistan War, and I don't want them to be in the same sentence, mixing things up. So we propose this first-order logic latent Dirichlet allocation, which is called fold all, to allow a weighted knowledge base of first-order logic rules. And if you're familiar with Markov logic networks, this is the idea that we're going to be using with LDA to incorporate our domain knowledge. And as in Markov logic networks or MLNs, we're going to have it such that these learned topics are influenced by the word document statistics, like in standard LDA. So it's just going to be trying to find topics that explain word co-occurrences, and the domain knowledge rules, just like in Markov logic networks. So you're going to try to get the best of both worlds, where the user can specify some rules that control the topics, but also it's going to generalize beyond that with the document statistics. So the first thing we need to do is represent the LDA variables in the logical context, which is pretty straightforward. If we say ZI is the topic assignment of the ith word in the corpus, we can make a predicate that says ZIT is true only if ZI equals T. Likewise for word I and document I. So now we have the observed words, the observed documents, and the latent topics represented as logical predicates. And we can go beyond that. Logical predicates are very flexible. We can define our own, like has label JL. If document J has label L, this is true, otherwise it's false. And we can include linguistic information as well, like sentences or part of speech tags. And this predicate logic formulation is a unified way to capture fairly arbitrary annotations, metadata, domain knowledge. So how are the user going to be able to formulate their domain knowledge, their constraints? They're going to make this conjunctive normal form knowledge base, KB, where each entry is a rule, which we'll get to in a minute, and a weight, which kind of signifies how strongly the user wants that rule to be in effect. So an example knowledge base for this biomedical application we're going to be sticking with is that maybe we have a seed rule where the user says anytime, if word I is embryo, if we observe the word embryo, topic I should be 3. All occurrences of the word embryo should go to topic 3, because I, the user, am kind of crafting a topic 3 built around embryo, stem cell, this kind of thing. Likewise, maybe we know that some documents are not really about stem cells or biology, and we say those documents are labeled plus. If the document is J, and J has label plus, do not use topic 3 anywhere in the document. So what if word embryo occurs in a document plus? That's okay. We can specify this kind of contradictory domain knowledge, and here the rule weights lambda will kind of control which of the two rules is going to win out. So to have these rules have an influence on the actual topic assignments, we're going to do something called propositionalization or grounding. So this example rule says that the words neural and disorder should never be assigned to the same topic. The user is interested in neural developmental biology, but not neural disorders or neural diseases. So they don't want these words ever in the same topic. So the free variables in this logical rule are I, J, and T, where I and J range over the corpus, and T ranges over the number of topics. So we're going to say G is the set of the ground rules for every single IJT triple. These I's range over the length of the entire corpus, I and J. T ranges over the number of topics. We're going to have an indicator function that indicates if a specific grounding is true for a given topic assignment. So if we have IJT, where I is neural, J is disorder, and they are the same topic, that grounding is going to be associated with a 0, otherwise a 1. So as in Markov logic networks, every grounding is going to be associated with a potential lambda times the indicator function, or e to that, the exponential of that. But the problem, as in Markov logic networks, is that this grounding is going to induce a combinatorial explosion. So if n is the length of the corpus, it could easily be in the millions or above. and t is the number of topics, which might be hundreds. So the number of groundings of this very simple rule could be 1,000,000 squared times 100. And this is going to cause us big trouble. So if you're familiar with graphical models, here the nodes are the variables, and the edges indicate conditional probability relationships. And this is the standard LDA model. And below is the probability distribution for standard LDA. We can easily rewrite this as a factor graph, which can be a little more convenient. And we can add this external factor, which is going to incorporate the MLN component of our model, and this extra O observed variable, which is our arbitrary metadata, like sentences or document labels. And then this red highlighted term indicates the impact of the Markov logic component on our joint distribution. So the task in topic modeling is usually to infer the learned topics, the latent topics assignments Z, the learned topics phi, which are the multinomials over words, and the document topic distributions theta. And the model, the algorithm we propose for doing this is alternating optimization with mirror descent, where it's basically going to be this iterative procedure where first we're going to learn the topics phi and theta, holding Z fixed, which is pretty easy to do. We're just going to need the map closed form equations. Then we're going to take the argmax of Z holding those guys fixed, where ZKB indicates the latent topic assignments affected by the knowledge base KB. So those rules that I specified before are not going to affect every single latent topic necessarily. So ones that are not affected by the rules, we can just do the argmax with respect to phi and theta, very easy. The ones that are affected by the rules, we need to take into account both the LDA terms and the logical rules. That's going to be very hard. Our scalable approach for doing this optimization involves relaxing the discrete problem to a continuous one. So each individual Z latent topic assignment is usually some discrete number. Zi is 3, topic 3 for the ith word. We're going to relax these to lie in the 0 to 1 interval. Then we're going to optimize this relaxed problem with stochastic gradient descent. And finally, we just round back to get the latent topic assignment. So to get the flexibility of MLN together with topic modeling, we have this unfortunately difficult inference problem due to the combinatorial explosion. And this SGD is how we're going to be able to still solve for the map inference for these latent topic assignments. So this is the log likelihood function that we want to optimize with respect to the latent Z. And we're going to be able to say that, okay, Zi equals T, Zit becomes a binary value. Is the ith word assigned to the tth topic? We're going to relax that to continuous. And these indicator functions for the logical formulas can be turned into polynomials which are equivalent to the original. So now we could theoretically calculate this full gradient and optimize. But this summation might still be enormous, so we might not be able to calculate the full gradient. So here we appeal to stochastic gradient ideas, where we're going to sample individual logic groundings from the equation. So we can just say this grounding of the formula, that grounding of the formula, and take their gradients. Likewise, we can sum onto that gradient the gradient with respect to the LDA terms. So we're doing stochastic gradient descent, essentially on the log posterior, the unnormalized log posterior, sampling both logic terms and the LDA terms. So that's how they're both going to exert their influence on the latent topic assignments. And this is going to be the update equation. So then at the end, we just recover it. So the experimental questions. How will we know if this is doing anything worthwhile? First, does the logic generalize to new documents? Do the logical rules affect the topics in a meaningful, durable way? And I'll explain what I mean by that. Next, can the alternating optimization scale? Will our scheme work for realistic corpora and rules? Finally, can we do something useful with this? The whole idea is to be able to learn these interesting topics and actually get some cool results. So first, we have these example data sets and knowledge bases, which you can see the paper for the details. I'm just going to give you the high-level idea. We're going to do k-fold cross-validation with each corpus, where we are going to use the logic rules to learn our topics on the training documents, and then use the topics only, not the rules, to do inference on the testing documents. then we'll evaluate that unnormalized probability to see if the logic rules are still obeyed. So basically, did the learned topics phi really capture something that our logic rules had been pushing it towards? So these values in the table, the rows correspond to the different data sets which are in the paper, and the columns correspond to different inference schemes. And the numbers themselves are proportional to the unnormalized probability on the test set held aside documents. So basically, the main thing to see here is that, yes, these logic rules are really captured in the learned topics phi in a durable way, such that the inferred latent topic assignments on the test set still obey the logical rules. So something about the rules is getting captured in the learned topics, such that when we apply the learned topics to new documents, the rules are still obeyed to a significant degree. The next thing to notice is that our baseline schemes, other than standard LDA, which does not use any logic whatsoever, are not able to scale to the problem of realistic corpora sizes of tens or hundreds of thousands of documents. And this is due to that combinatorial explosion issue we had talked about earlier, and the way in which it interacts with the LDA terms. So the dash indicates that a run was not able to complete in 24 hours, which was considered unacceptable for our purposes on these relatively small data sets and experimental iterations. So on the realistic, the larger data sets, our algorithm is able to scale, and the topics do capture something interesting. So now we want to actually do something cool with it. So we have a biologist who is interested in expanding some concepts that he's going to define with seed terms. So he gives us seed terms for these human stem cell concepts, and he wants to grow them out with topic models. So we're going to focus in particular on the neural topic, where we're going to use a seed rule, like I said before, where all instances of synapse go to topic 0. One other cool thing we can do with logic is we can actually specify n-gram labels as well within the logical framework. So inner cell mass is going to go to topic 1 only when we observe it as a trigram in this way. So this is really cool, and there are other topic models that can do this, but we can just do it within the logical model without hacking on LDA directly. We're also going to add these sentence rules, which are going to allow us to incorporate sentence level information, such as we're going to make a new development topic because that's what the user is really interested in, and try to make that development topic co-occur with our neural topic as well. Likewise, the user is not interested in disease, so we're going to use this sentence level information to say, don't have my neural topic co-occur with my disease topic in the same sentence. So these are other things that the biologist kind of suggested. And the results are this, where the number here is the accuracy at the top 50, and this is in blind relevance judgments by our biological collaborator. Of the top 50 words, how many are really related to my concept of interest? We're at the far right, we have standard LDA, and as we move to the left, we have increasingly sophisticated logic rules based on feedback from our biological collaborator. And LDA doesn't do that great, but as we go further with more and more logic rules kind of based on feedback, we're able to do better and better and recover interesting terms that the biologists thought were useful. And these are some example terms that were recovered only by the fancy sentence inclusion logic and the full knowledge base, which were really interesting technical terms that the biologist looked at it and said, yeah, that's definitely related to what I'm studying, but I wouldn't have thought to write those ones down. So this is some qualitative and quantitative validation that our approach can do something cool without any graphical model hacking whatsoever beyond what we did to get the logic to work in the first place. So with that, I'm going to wrap it up. The idea here is that we're able to do domain knowledge-enabled topic modeling without forcing domain experts to hack on graphical models, which we think is a big win. In order to do that, we had to derive kind of a new scalable inference algorithm, and the experimental results showed some interesting stuff that it basically worked. So I'd like to acknowledge my funding sources and thank you all for listening. Source code is available.
Why not use the logic rules? Oh, I was saying, nice work. Why not use the rules at inference time as well? You just use them at training time, right? But then at inference time, you just use the model that you learned.
Oh, okay. So in LDA, we're just doing inference basically. So the whole test set, train set thing was only to evaluate if the rules kind of stuck.
Okay. Yeah.
Any other questions? Okay, I have one. If you go back to, you made an example. Right. You made an example about a rule in which you could specify the co-occurrence of several words. Like this one, right? Wouldn't that be much simpler to have, rather than a simple bag of words model, a terminological model where you first acquire those co-occurrences rather than specifying those as terms? Because another question which is implied with this, how easy is for the user of this model to specify these rules in logic form?
So
how much easier is with respect to specify which topics?
So certainly if we had, we have this kind of pre-canned set of rules like this n-gram rule or the seed rule, where it could be as simple as having somebody write you a Python script that takes your list of n-grams and spits those out into rules or something like this. Certainly, even writing the rules out is going to be still a lot easier than hacking on the LDA model to make it obey kind of what you wanted it to do. As far as using co-occurrences, you could do any pre-processing you like you said, do like statistical co-occurrence, and then use that to populate the rules if you wanted. So these rules could definitely come from automated methods as well as handwritten if you wanted to feed that into LDA as well.
Okay, thank you.
What's the syntax of the rule you use?
So it's general first order logic. If you want to specify your own brand new predicates, there's something you have to do. But basically, if you want to use any of these rules I talked about in the talk or the paper, there's just a very simple column delimited thing if you want to check out the source code or the paper.
Do you use disjunction or existential quantifier in the rule?
The quantifiers are all universal. It's very similar to Markov logic network. So all the rules have to be in conjunctive normal form.
Okay.
The knowledge base does, rather.
It's like Holland logic.
Horn logic. It's been a while.
Yeah.
Yeah.